Hi, welcome to my channel once again. Today I'll be doing an extended version of the vector error correction model, and I've already loaded my data into Gretl. So we are using time series data. You can check from here from 1993 to 2022 for all the variables. So without wasting my time, I'll first of all also move to this part which I have some data here, and also I have already listed that we need to do var lag length installation, and also we will also do something about unit root co-integration, and the last thing is the vector error correction model. So what we need to do now is that some people would like to start with the assembly statistics, but I don't know if at this point we should do it or maybe move on. Probably let's try doing the assembly statistics so that we will get a complete thing that we are supposed to do today. First, just go to view and you can see assembly statistics. Then I will put all the variables here accordingly. I have a spot inflation to real effective exchange rate. Then click on, we need only the main statistics. So this is our semi statistic that we had. From this point, we can just copy in this format. So click on OK. And then when we come here, I can equally paste it down here. So let's see what happens. Paste. And it gives us this. You can see it's giving us this, but let's see what we can do. So let's add the borders to it, or borders. And here you can see that it's giving us plus 0.3. So it couldn't bring all the numbers that we need. So you can just retype everything here and also do the same thing for this part, which is 634. And then what is the last? Also we have this, and the reason why we're having this big values for this one is that we haven't convert anything to logs and they are in their natural state. So I'm just trying to change everything to as it is in this format, and we have the maximum to be 15. Okay, so let's do it this way, which is 975. So this is our assembly statistics using all the variables, and I can delete this one because we already know that we use all the variables. And also after this one, I can close this because I don't need anything from this part again. I'll go to view again and also do for correlation metrics. Then I'll select this one. You can do the same thing according to how you want it, but usually I want my dependent variable to be on top so that the independent variables will follow. Then I'll click on OK, and this is our correlation matrix. I'll copy everything. Let's copy everything from this part. Copy this format again. Then I come down here, paste everything, and as you can see, usually I don't want my table to be divided, so I'll push this one down. Just add over this and you have your this thing done nicely. So you can just name it, or should I use this cap? So this is our correlation matrix, and I think we can now move on to the next steps, the most important steps. So first of all, what do we need to do? We need to perform the var selection. So we must go to model and multivariate time series. You can see it here. Select this one, input all your variables here. Let's go for maybe trade openness and FDI and inflation. So let's increase the lag to, let's say, lag 4. And as you can see, we have lag 4 to be our optimum lag to be used in the vector error correction. So, and the Johansson cointegration if necessary. So what we need to do is that we need to transfer this information to our table, and then we can interpret it. But before then, okay, let's do the interpretation here. First, we are comparing all the lags and then select the one which is match optimal for our model estimation. But let me give you one clue. Always see where the asterisks are pointing to. When you check from this place, you can see that under this part, under AIC, which is the Akaki information criterion, you can see it is pointing to lag 4, and you can see the p-value. The lowest p-value shows that the lag 4 is the optimum under the Akaki information criterion. The BIC, which is the Bayesian criterion, also pointed to lag 4, showing that lag 4 is the optimum lag to be used, and then the Hannan-Quinn also is pointing to lag 4. So based on this, we can conclude that lag 4 is the optimum lag to be used in our model. And in this case, you just need to transfer all the information you have here, and some of them can do 3 decimal places, and that is how I want mine. But since they are 3 digits in front already, I'll choose only 2 behind. So you can equally also paste all these ones, and please do the same thing, paste according to how the table is arranged or how you constructed your table. And here is supposed to be lag. Put your lag 1, lag 2, lag 3. Oh, sorry, lag 3 should be here. Then we need to add additional lag to it, which is a lag 4. And also here, since there is no p-value, you can put none or dash. And here you can copy, you have to copy because we have already created a table for them. And here you can see that we have this. So this is okay. Let's leave it 2 decimal places and copy this one. But you can, everything depends on you, the estimator, the person who is conducting the research, how you want your values to look like. And also we have this. I'll paste this one to here as well. And I think this one need to go for the lag 4, which is here. So we need to copy the p-values. I think some people would like to argue, so let's put everything for the p-value so that we can do the differentiation among the variables or among the lags that we selected. Sorry, not variables, but among the lags here displaying at this point. So we have everything here, just paste them and also put the asterisk here to show that this is where it's pointing to. And you can also copy for the rest of them the same step. Then everything should be copied. Everything should be copied. Make sure you copy everything, paste them, just paste them and let them look really good. So everything needs to look really good. paste everything. Let's put this thing here because this is where it's pointing to. And let's copy for the last column, which so let's not take it. I didn't do runoff, so I just leave it the way it is and don't do the runoff. If you want, you can do it. For mine, there is no runoff here, so I'll paste this one too and then put this here. So now once we know that this is our lag length selection, we can say that this is done. So let's say done, or you can take it. Then the next step is that we need to move on to unit root. But before we can use the vector error correction here, please let's note that our variables, all the variables must be integrated at first order before we can use the vector error correction. If the variables are made up of I1 and then I0, then we cannot use the vector error correction. We have to use the ARDO model. So I have not tried the data, but immediately we find anything that is which is integrated at order 0, then I believe we need to pause, or we need to eliminate one of the variables which is causing or which is integrated at I0. So let's continue. After this, we need to perform the unit root test. Some people might choose to add logs, but for me at this point, let's not add any logs for the moment and try to do the unit root test. When we are moving to the vector error correction, we can add logs to our variables, but if you want, you can also add logs right from the beginning. But at this point, I prefer we do it this way. But like I said, everything depends on you, the estimator. So let's start with trade openers, and you can see I've already entered them here. So let's start with this one. So go to variable, go to this and augmented, and we need let's increase this to lag 2, and also we need text without constant, test with constant, and test with constant and trend. These are the three main variants under the ADF unit root test, and if you want to know more about it, try to watch my other videos on the channels which is talking much about the unit root test. And here we will have to show regression result and also click on OK. And as you can see here, we have the test with constant and trend, which is giving us a p-value which is greater than 5%, and we need to know that a p-value greater than 5% shows that there is a unit root. A p-value which is lower than 5% shows that there is no unit root. And as you can see from this side, this is even also exactly 5%, and we can see there is a unit root because it is not lower than 5%. And here too, you can also see that there is a unit root. So we can actually copy from this side, which we need. This is the ADF T statistics, and as you can see here, you can see there's a test statistics here. You paste it. We need the alpha -1, which here you can see here, this is this place, that is the critical value that you need. Paste here. So here the p-value we need to put here is 0.63 or 0.64. I don't know if somebody might choose to convert it. So this is for at levels, and the sample size, which range did it run the data from, you can see 1994 to 2022, you can put it 1994 to 2022. Usually you can also choose to ignore this part because it is not mandatory for you to put all these things, because sometimes when you run the first difference, it's usually also going to either reduce the sample size or increase it. So it is not necessary for you to include this part here, but you can also explain it in your result. So let's add first difference to trade openness. You can go here, add, and you can see first difference of selected variables. We have added it. Now let's select this one and go to unit root test again. So we go to augmented and we are using the same format, but here you can see we have already converted this one to first difference, and even though this place it is taken use level of variable, it is not going to use that because we have already converted this one into first difference. And as you can see here, since we are using the first difference, look here, it shows that there is no unit root. Here it also shows that there is no unit root. You can pick any of them because they are all the variants you can use. So someone might choose to use this one, which you paste the p-value here. Then you select this one, which is the ADF, and also you select this one, which is the critical value alpha -1. Then you paste it here, and here the order of integration you can put I1, because the reason why we are putting I1 is that we only add first difference to the variable, and then we had a unit root not present in the variable. And here it shows that at first difference, trade openness has no unit root, but at level there is a unit root present. So with this one, we are done with trade openness, the unit root test for trade openness. Let's move on to the other variable, which is inflation. Usually inflation, I guess, always sometimes doesn't have a unit root at level, but let's see. So let's see from this part. You can see from this part, you can see that straight away inflation doesn't have a unit root. It doesn't. And this also shows that we cannot use the vector error correction. But let's see something here. Sometimes it also depends on the lag that you're using. So let's go to this point and see again. Let's try to increase this lag to, let's say, lag 3 and see. So you can see that the more we add a lot of lag, the more it becomes more significant. So here we can also try again and check this one. Let's change this one to like 0 and see. Now you can see the p-value is 0, 0, 0, 0 because it doesn't work without this one. So we need to also go back here again and increase the lag to, let's say, lag 4. See what happens. Now you can see the p-value has started coming out, and you can see from here. So the number of lag you use also determine the unit root test you're performing. And I'm trying to give you a clue because at lag 1, somebody might say that it doesn't have a unit root, but if you increase the lag, it shows a unit root present in it. So let's just try. The assumption is that let's just try that we increase the lag by trying to test all the variables. But under normal circumstance, for me, I would have eliminated inflation from it. But since we have already loaded everything here, we just have to test everything together and see how we can interpret our results. But when we're doing it in a real situation, make sure whatever variable which is integrated at I0, which is auto 0 without any differences, make sure you apply the ARDA model, because ARDA model, it also factors in where you can use I0 and then I1 variables. So always, if you want to use the vector error correction, please try and stay away from inflation rate, because sometimes even at levels it has no unit root. So just for practical sake, let's just try to copy this one as our p value we had and paste it here, and also copy these ones and paste it as our ADF statistics. Like I said, the reason why I'm not focusing on the dates anymore here, the sample size, is that it's not always mandatory to put this thing. You just need this part. So for this, I also copy the alpha and paste it. Then this one here, we are done with the first part at levels. Let's go for a first difference in this. So let's add a first difference in this and then try to rerun it again. So we go to variables and then go to unit root, select augmented, and then click on OK. Now you can see it's completely integrated at first order. So you can equally, instead of putting this, I can just copy this one, then I'll paste it, and I'll also copy this one and paste it here. So for me to write all these things, it means that it is less than 1%. So I can just put 00 and say that it is I1. Then we move to GDP per capita. So let's try to do it for GDP per capita. GDP per capita. So GDP per capita, let's try to select that one. Go to variable, go to unit root, augmented, and also we can also leave it here and see what happens. Like I said, always the lag has a very, very, very important role to play in whatever you do. Here, even with all the lag for, let's see something here. There's still a unit root present. And always remember that the alpha minus 1 can never be higher than the ADF test statistics. So pay attention to that one. So we can copy from this, as we know already. Copy this one and paste it. Oh, I think there's a mistake here. You can see the p-value is supposed to be here. P-value is supposed to be here. So it's supposed to be 0.727, if I'm not wrong. Let's take it that way. So, and also we copy this one, then paste it here, and also we need the p-value, which we will paste here. So we have filled for the at levels. I can equally take this one off by deleting it. So we have filled for at levels. Now let's do for first difference. Let's go here add first difference to this. Then we select this one and go to unit root. Again, try it again and see what happens. So you can see it has been integrated at first order. You can see here, as you can see, and there are 3 different variants. You can use which one suits you. So let me use this one here again. Okay, let's paste this one. Let's also copy this one and paste it here, and also copy this, paste it, and then here is going to be I1. Then the last step is to do for real effective exchange rate. So now let's select that one, go to unit root again, click on this, and let's try again and see. And this one, this variable, let's see what happens here. You can see here the time trend, which is a trend, is significant at 10%, and the constant is also significant. So usually if you want to use the time trend, the time, which is a trend, or the constant and trend, these two must be significant and the p-value must show that there is no unit root. That is the basic assumption you're supposed to use. But like I said, there are 3 different variants, and whatever suits you, just use that one. So let's just put this one here too and see. We have this, we copy this one, also we paste this one here, then we copy this one and paste the p-value here. So we need to close this one again. Then we need to also, after closing this one, we need to add first difference. So we're going to add first difference here, do it on the first difference. So go to variable again, then go to unit root, and also let's just try again and do it. Click on this. So you can see the p-value is almost here, it's at, let's say, 1% or getting to 2%, and here it's at okay, this is less than 1%, and here it's less than 1%. So here you can see here with constant, the constant is not statistically significant. So on the normal circumstance we couldn't use this one, and here the trend, it is not significant, and also the constant is not significant. Usually if these things going by the normal standard procedure like what I've mentioned right now, you should have used this one. But since we have stick to this one already, let's just try and copy this one, which I'll paste here, which is the p-value. Then copy the statistics, paste it here, and also copy this one and paste it here. So this is going to be I1. Now whatever we've done, I have to save it. So I can just save this one so that maybe in case of anything can happen, it's a system that we are using. So now let's continue with this one. So once we are done with the ADF, we can move on to the Johansen co-integration test, because this one, all the variables are integrated at first order. That means that we can equally perform the Johansen co-integration test and also move on with the vector error correction model. So what we need to do is that we have to close everything here, and here I don't need the first difference or anything right now. I don't need them. And is there any other variables which is missing? We have trade openness. Oh, there's FDI, which we need to do for FDI. But you can, okay, let me just do it because in order to avoid any confusion, let's do it for FDI as well. So let's go for FDI variable. Then the filler, we select this one, and you know certainly that there is no sign of showing that unit root is not present. Indeed, there is a unit root. There is a unit root here. So we copy the p-value, paste it here, copy the ADF statistics, and then paste it, then copy this one and paste it here. So let's close this one and add first difference to FDI. So you can equally select all the variables and add the first difference to them, but since we are doing it, I just wanted to do them one after the other so that you will get the logic behind everything. So I selected this one. Let's perform, go to variables again, then click on this one. Since we are using we have already converted this into first difference, you don't need to select use first difference of the variable because it's already in first difference. So let's click on this one, and as you can see here, the variable is really integrated at first order. So instead of copying this whole digit 4 point these, I will just put 00 because it's less than 5% and also less than 1%. So you copy this one as well, copy everything. Make sure you copy everything here. We paste this and then we put 00, 0.00, and we put I1. So now save this and let's move on with the next step. So here I don't need these variables again, which is the first difference. I can equally select everything, then delete them. It doesn't affect your original data here, so I'll just delete it. It will ask me, and I said okay. The step is that we need to go to the Johansson co-integration test, go to model, multivariate time series, and you can see co-integration test interact with Johansson. So let's do it this way. Now one may ask, let's do it this way. I can equally do everything one after the other, and then put this one as well here too, and let's say we are using lag 4 and see what happens. So we are using lag 4 using the variables at level, and you can see here the null hypothesis of Johansson states that there is no co-integration. So I've already done a video on this. You can equally go and check that, which is the HO. Let me put this and so that somebody will understand. HO, after this, HO equals to no co-integration and we can put H1 here, which is the alternative. So and also equal to okay, let me write it in a simple way so that people will understand. So here, no co-integration exists. And you have to understand that immediately you reject the null hypothesis, you need to go for the alternative hypothesis. And for you to accept that there is co-integration, the null hypothesis need to be rejected. And a lower p-value count against the null hypothesis. So if the p-value is less than 5%, which is the critical value that we are using for the entire analysis, automatically we need to say that there is co-integration. So in my other videos that I've done already, you can cross-check them. Everything is explained there. So here we need these values, and we have rank 0, rank 1, rank 2, rank 3, and then we have rank 4. Rank 4, which is the fifth one. So we have 1, 2, 3, 4, 5, because we have 5 variables. And here we need to fill everything. The reason why I'm doing all these ones and I'm not skipping anything is that people really want to understand how they would be able to fill their tables and those stuff. So I just wanted to do all these things so that when you're filling your tables, don't forget these things. Make sure everything is needed. So we copy this one too, and then we paste them here. Then we need to understand that under the Johansen co-integration test, we have the trace test, and then we have the likelihood maximum test. So here on your left, you have the trace. On your right, we have the log likelihood maximum test. So we need to compare all of them and see. So this is the trace test. I'll copy this one and I'll paste it here. You can see the table also have a trace test here. I'll copy everything that I need here. I'll copy them here. Copy them here. And let's see. Copy them here. Everything we need must be here. So we are copying everything from this point to this end. I mean, we need everything here. So just copy everything like I'm doing. Don't feel lazy. Do everything we need at 3 decimal places. So you can see all this place. We have 0. We have 0 because, and here we have, let's say up to 0.9. Like I'm not doing runoff. And here you can see that we have this. You just need to copy and paste it. And also we need to copy for the likelihood maximum test, which is also here. Paste it, copy this one, and also paste it here. Like I said, this thing doesn't come in a table form. You need to create your own table for it. So whatever table you see here is my own tables I have created, and I've been using this often. So just copy this one, copy everything, and then paste them here. Just paste everything. So the next step is that we need to copy from the p-value option. Copy everything, and let's see here we have 0, 0. So I can paste 0 here too as well. And we have another 0, 0, 0, 0, but there is 3 at the end, and we have here 0.01, which is let's say practically 1.1%, and we paste this one here. The last one, usually these p-values are the same, so you can see it's the same. So now we have our Johansson co-integration values that we need. So let's check here from the word and then try to decide on everything. Using the trace test, you can see it produce a p-value of 0.00, and the likelihood maximum test also produce a p-value of 0.0. So here we can say that we reject, this is rejected because the p-value is less than 5%. This is also rejected, so we can just copy everything here and paste it here. Rejected, rejected, and the last one is not rejected because the p-value is greater than 5%. So not rejected. So whatever happens here is that we have 5 different ranks. When I say 5 different ranks, starting from 0 to 4, it's 5. So it means that 4 of the ranks are rejected, which states that there is no co-integration, which goes with the null hypothesis. So if you are rejecting 4 out of 5, it means that there exists long run relationship between the variable, because 4 of the ranks out of 5 is being rejected. And like I said from the beginning, immediately we reject the null hypothesis, we need to go for the alternative hypothesis. And here at rank 4, we couldn't go for the alternative hypothesis because we were not able to reject the null hypothesis. So we can conclude that out of the 5 ranks, 4 of them state that there is no co-integration, which we have rejected the null hypothesis and then stick with the alternate hypothesis. So we can conclude that there is co-integration among or between the variables, because we have rejected the null hypothesis from rank 0 up to rank 3, then going for the alternative hypothesis, which is co-integration exists. So here we can conclude that there is co-integration among or between GDP per capita, real effective exchange rate, inflation, FDI, and trade openness. That is the interpretation. In a situation where you find the p-values, all of them, to be greater than 5%, or even if you find at rank 1, rank 0, rank 1, rank 2, and then rank 3, the p-values which are greater than 5%, then if the last rank only have a p-value that you are rejecting, it means that there is no co-integration, because always majority must carry the day. And here the reason why we are saying that there's co-integration is that we have rejected 4 out of the 5 ranks here from the co-integration output. So once there is co-integration, let's move on to the vector error correction, what is the main deal that we are supposed to do. And before we go to the vector error correction, here I advise we can convert our variables into log and then try it. Sometimes you can also leave them this way, but I believe we can convert them into logs and then try it here. Because when you convert the variables to log, it gives you a baseline of measurement. Because already when you check GDP per capita, it has bigger values, and at the end of the day, it is going to influence the coefficient or the coefficient here. So let's get a standard baseline, which is converting everything to log. And like I said here, I'm going to say something here again. Let's check the values here. FDI has a negative value for 2022. Once we convert it into log, this will get missing, but it doesn't matter. Vector error correction here will factor in that option. But when you're doing your limitation or deficiencies of the research that you've conducted, you can also state that. So let's continue by selecting everything, go to add, and then Here we need to add logs. So you can see generated missing values, and the missing value, I think it's gonna come from, you can see there is nothing missing here, and here there is nothing missing here as well, and inflation, there is nothing missing. You can go to FDI and you can see 2022 is missing. So we can also check for trade openness. You can see there is nothing missing. Now, since we are done with co-integration, let's move on to the main thing we are supposed to do for today, which is the vector error correction model. So now let's go to multivariate. Then we go to this part and select this one. So what do we have to do? One thing we have to understand is that we are using the vector error correction here. So we need to, like I said, we converted everything into logs. We need to remove whatever is in levels. So remove this one. And the rule is that whatever lag you have is -1. So here, instead of, we cannot use lag 4, we need to use lag 3 here. And also the next step is that I need to put the variable which I think will be my dependent variable, which I'm much interested in, which is the GDP per capita, and also per capita, and also let's put trade openness. We have put in, we can also select every independent variable you like randomly, not necessarily, or you can also arrange them the way you want it. And here the condition is that we are using endogenous variables, and here, since we have 5 different variables loaded here, we are going to get 5 different outputs, which we are supposed to get 5 different error correction terms. The reason is that it is tested from both or all directions to find where, in case of any deviation, the variable need to adjust back to equilibrium. So here it is going to test using GDP as the dependent variable, and later on it will take real effective exchange rate as the dependent variable, and later it takes trade openness as the dependent variable, and also it takes FDI as the dependent variable, and also take inflation. So let's try and click on OK. Now once you click on OK, just check here. What do we see here? Let's try and then do some interpretation here and see. Now look at this. You can see here our main variable of interest, which is the GDP per capita. You can see that GDP per capita, the constant, is not statistically significant, so we cannot say anything about it. But at level 1, which is 1 period or 1 year ago, so lag 1 means lag 1. Okay, we can also, let's copy everything and then we will extract whatever we need from this place. So I'm going to copy everything here, copy, and let's go down. I think we already have this, some items here. Let's go down and I'll paste everything here. So let's paste this one. I don't need this headers from the whole of this place to there, so we need to delete. I'll delete this one. Everything is deleted, and just add your borders to it. Add borders to it. Add borders. Then you can also add borders to this one. Add borders. Then add borders. We're doing it for everything here, so let's try and add borders to everything here and try this. So I don't need this one. So now I have these things here. What do we need to do here? Let's try and do the interpretation. Like I said here, for instance, let me give you a clue here. That 1 equals to okay, I think I'm typing something wrong here. So never mind. So we do all these things for the same thing. And let's say, for instance, I will still explain something as we finish with this interpretation and we try to understand something. So here we try to explain whatever information we have here. For instance, we have the equation 1, which uses GDP per capita as the dependent variable, and you can see from this side that the constant is not significant, but GDP per capita 1 year ago is significant, and the coefficient is positive. Sorry, it's positive, but it's significant at 10%. When you see this okay, the star 1, when you see a star, which is this, no, I think not this way. When you see this star, let's say 10%, let's consider this to be 10%. When you see this 5%, and then when you see this, people use this one as 1%, and usually you have to know that the 3 stars or asterisks you see here is showing that it is less than 1%, and here it is less than 5%, and here it is less than 10%. That is how the indication is, because when you check the p-value here, it shows that it is less than 10%. That's why you have 1 star. So what we need to do, what we can say is that a unit change or a percentage change in GDP per capita indicates that let's say previous 1 year ago. So here you can interpret this: previous 1 year ago has a positive effect on the current GDP per capita, and this is because of this p value, which is significant at 10%, which is less than 10% that I want to say. So at this point, there is nothing for us to interpret here, because nothing is significant here. So let's try and look for something which is really significant, which has significant values, and try to explain them. Here, GDP per capita previous 1 year ago has a positive effect on real effective exchange rate. and the percentage change in this one has this effect on real effective exchange rate. I hope this is a little bit clear. Take it this way. If it's a percentage, it means that, let's say, a percentage change will have this influence on this one because it's significant, because it is significant, because this one is significant. That's why we say that. And you can see from here, the rest of the variables are also not significant. You can see here, real effective exchange rate itself does not influence the current, the past one does not influence the current one, because all these p-values for real effective exchange rate are not significant. Now let's check something from FDI. You can see here, look at this place. Here, FDI has a negative coefficient and the p-value is statistically significant. So the p-value here shows that the sign is what we use to interpret it. The sign attached to the coefficients is what we use to do the interpretation. Here you can see previous 1 year ago has a negative influence on real effective exchange rate because we are dealing with previous years ago. Look, this is 1 year ago. The lag shows 1 year ago, as I've explained here. Lag 1, previous 1 year ago. Lag 2, previous 2 years ago. So it keeps on increasing. When it goes to lag 3, you say 3 years, previous 3 years ago or 3 years ago. So here you can say that FDI, previous 1 year ago, FDI has a negative influence on real effective exchange rate, and previous 2 years FDI, like let's say previous 2 years ago, FDI has a negative influence on real effective exchange rate, or has a negative relationship with real effective exchange rate. And here the assumption is that the error correction term at lag or period 1 should be negative and statistically significant. But as you can see here, look at this place. The coefficient for the error correction term, it's not negative, but it's statistically significant, and this doesn't show any sign of, in terms of when there's a disequilibrium, there will be any adjustment or there will be any speed of adjustment. It doesn't give any meaningful interpretation, because this here is not having the sign we anticipated for. So we cannot confirm that there will be any speed of adjustment between these variables using real effective exchange rate as the dependent variable in the equation 2. Now let's try to go to equation 3 using trade openness as the dependent variable. So let's see, in the equation 3, you can see here a lot of things are very, 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 very significant here. The constant is significant. GDP per capita previous 1 year ago has a negative. Look, the coefficient here is negative. The p-value is significant, and so we can say that it has a negative relationship with trade openness. And you can see 2 years ago, I don't think it's significant. Check here, the p-value is not significant, so we cannot say anything. Doesn't have 2 years ago, doesn't have any relationship or doesn't have any influence on trade openness. Look at real effective exchange rate. It has a negative effect, and you can interpret that previous 1 year ago real effective exchange rate has a negative relationship with trade openness. And here you can also say that previous 2 years ago has a negative relationship. And trade openness, you can also state that it has a negative relationship, and previous 2 years ago also has a negative relationship. And you can also state that FDI previous 1 year ago has a positive relationship with trade openness, and previous 2 years ago has a positive relationship with trade openness. And look at inflation. Inflation here also has a negative relationship because the coefficient is negative for both lags, lag 1, lag 2, lag 3. So you can see that most of the variables has a negative relationship with trade openness. Now here comes the main thing we are looking for. You can see that the error correction term is negative and statistically significant at less than 1%. So what we can say here is that in terms of any deviation, let me go this place. In terms of any deviation, when you see the EC1, which is the error correction coefficient, which is the minus, let's say minus 0.07, let's say 3, or some people will say 4. Let me say 3, so that it will not confuse people. This coefficient that you see, in terms of any deviation, the speed of adjustment so here, in terms of any deviation, when you convert this one, you multiply this one by 100. Let's say when you convert this one to 100, automatically you get 7.3%, even though we can see the negative sign here, but we are multiplying it by, let's say, 100. This is what we should get. This is 7%. So in terms of any deviation, this is multiplied by 100%, and let's say it changes one to percentage. To change this one to percentage, just multiply it by 100%. Let's say 100%. So you get this, which is the speed of adjustment that need to happen in order to bring the variable back to equilibrium. The error correction term talks about the deviation and the need of adjustment from the short term to the long term. So if anything happens, if a deviation occurs or a disequilibrium occurs, the variable need to adjust by 7% in the preceding years in order to get back to equilibrium. So this is how it works. So now let's move on to FDI as the equation 4. You can see that there is nothing really to talk about, but you can see that past FDI, which is previous 1 year ago, has a negative effect or has a negative relationship with the current FDI, because it is influencing itself. So now let's move to the last one, which we can also talk about here. You can see that the constant is significant and GDP per capita, lag 1 and lag 2 are all not significant and we cannot interpret it. It means that they don't have any influence on inflation. But let's see, look at real effective exchange rates. Lag 1, lag 2, it shows that they all have a negative relationship or a negative impact, because look, they are all significant. The coefficients are negative. So please always pay attention. The signs attached to the coefficient are what we are using to interpret it. So if it is negative, it means that it is decreasing. If it is positive, it means that it is increasing. So looking at this being negative, so you say that there is a negative relationship between the past real effective exchange rate, which is 1 year ago, with inflation, and 2 years ago, previous 2 years ago, has a negative relationship with inflation because the coefficient is negative. And also look at trade openness. Here it is not significant at this point, you can see, but the lag 2 shows that it is significant and it has a negative relationship or a negative impact on inflation. And look at FDI, it shows that it has a positive relationship with inflation, and the lag 1, that is the previous 1 year ago, and then previous 2 years ago, also has a positive relationship with inflation. And when you talk about inflation itself, it says that previous 1 year ago, previous 2 years ago has a negative relationship with inflation itself, or the current inflation. So we are using the coefficients to determine the relationship or the impact the variables exert on the dependent variable. Now look at the error correction term. The error correction term, which is the EC1, which is the error correction, EC, which is the error correction, correction coefficient, which is into bracket minus 0.946. Okay, let's take it this way. Means that, sorry, so okay, okay, so let's say this is the interpretation you can give. And also somebody will say, okay, once we have this, So another situation when you had an error correction coefficient around or not around, let's say around 1 and between maybe 2, or it can go more, maybe 2.5. It's not wrong. You are not wrong, because in this situation it says that when when a disequilibrium or deviation happens, it means that the economy cannot recover within 1 year. That is one thing we have to understand. The economy cannot recover within 1 year. So these are the things we need to consider. But usually, people are always looking at a coefficient which is less than 1. But we have to understand that in terms of any deviation, does the economy really recovers within 1 year? That is one thing we need to understand in terms of economic activities. And here too, you can also see an R square here. The R square says that, look, the R square for this one, R equals to 0.8, 0.8, let's say 2. So this is how you should interpret everything. So you can also adjusted R square will be 69%, and the R square will be 82% or 83. So you can interpret your R squares. This is 42, and this is 42, and this is, it says the minus, because you have to know that R square can be 1. It can be between 1 and -1. So you can also interpret this one. And also the same thing goes here. This is 91%, this is 85%, and here it is 82, and you can see 69, and also you can also see 38, and you can see minus 0.9, 0.09, and that is it. So this is all about the vector error correction, but you're not done. So here, once we are done running this result, we can also do some diagnostic tests, and we can also plot for autocorrelation. Let's say when you go to 2, you can see here there is none because the lag is too much. So we can, here using lag 1, we can conclude that there is no autocorrelation among the or autocorrelations in the result that we've run. And we can also do for ACT, which is auto-regressive conditional heteroscedasticity. Let's use 1. You can see there is nothing here. It says that it is free from auto-regressive conditional heteroscedasticity. And also we can also do for normality, and you can see here, always focus on this one, Donick-Hansen test, which shows that the p-value is the one in the bracket, and you can see that a p-value greater than 5% indicate that the residuals are normally distributed. So you can see perfectly from this place that there is nothing like the residuals are not normally distributed. Indeed, they are normally distributed because the p-value is greater than 5%. So we can say that there's a normal distribution of the residuals. So these are the tests you can conduct once you perform these ones. And also, let's try to understand one thing here. You can see we use like 3 here. Let's say even if we put like 4 here, when you put like 4 here, you are still going to get 3 because it's always taking 1 out of the number of lags you're putting. So let's check this point. You can see matrix is not positive and definite, so it's not possible. We have to use lag 3 because it's -1 here. That's why we are using lag 3. So don't get confused. And this is all about the vector error correction. But before we go, let me give you one clue here. There's one thing you shouldn't forget about. You should always run multicollinearity, which also states that no variable should be a perfect combination of each other. When I talk about the perfect combination of each other, it means that one of the variable is capable of explaining each other. So those variables cannot be in the same equation together. So when we want to run the test again, let's try to run the test again and do what I'm talking about. So here we do this, and then let's do analysis. So you can see here, you can see impulse, you can see this, you can run this, you can do all these things. You can go to graph and try to plot this one. This is very important. You can do the easy plot and look at how the movement goes. And also you can usually also do this one, which is, look at this one. You know that you know the axis. So you have your x, you have your y. So let's say when you go to the y, here is positive and here is negative, and here you have the y, we have the x to be positive and here is negative. So whatever values you get, it will be able to show you here to determine the angle or triangle you're supposed to plot from this one. So this is one thing about it. You can also do your normal analysis about this one and plotting your graphs as well. And you can also plot, you can also use it for forecast, which I'm not going to do. And you can as well as run for decomposition and other stuff here. So there's one more important thing, which is the multicollinearity I talk about here. Let's say I want to run a multicollinearity test. You can see here there's a collinearity here. Let's say the variables are at levels here. Let's try and run them. Do you have to include constant? Yes, because our model, we have constant in it. So let's try to check. Look, it says that the cone right here, everything is being explained here much better. Here there's a cone variable or a cone value which is exceeding 30, and the minimum value is 1, and it should be between 10. So look at this place. Since we are using the variables at level, it's saying that there's a multicollinearity, or there's a collinearity among the variables. But mind you, and remember that the vector error correction, it's using first difference. So in order to match up with the variables you're using, you can as well as also add the first difference to your variable before you run the multicollinearity test. So because the variable, look at this point, whatever we run here, the d you see is the difference. So if you indeed you want to run a multicollinearity or collinearity test, you have to use the first difference of the variables. So let's try here and see. You can as well as do this, or you don't need to finish your results. You can also, so one may also ask, what if I don't add the constant? Okay, include constant? No. So you can see it reduces the number of the value or the figure for the cone, but that is not the best way to do it, since it is taking the first difference of your variables, you need to add first difference of your variables. So let's say first difference, and let's try to run it if it is going to work. So let's see. Now you see everything work perfectly because we are using first difference to run the models. So multicollinearity here which you're going to use need to be run using the first difference. I believe this has been a helpful video for you, and don't just watch the video, try and practice at home and make sure you practice very well and become perfect in everything you're learning from this channel. Thank you very much.